Jupiter, that colossal world, a place known for its immense storms, its dangerous radiation, and a truly captivating kind of beauty. It's a powerhouse, a giant whose sheer mass is so great that it actually pulls on the Sun itself. This gas giant is quickly becoming one of the most studied objects we have in our entire solar system. Think about it. We've sent 7 missions flying past it. 2 orbiters have circled it, and one of those is still hard at work right now. Plus, there are 2 more missions already planned to head its way. There's just so much for us to uncover about this 5th planet from the Sun. We wonder, for instance, what gives Jupiter its really distinct reddish colors? What exactly is it made of, deep down? What secrets are hidden beneath those thick, obscuring clouds? And what do we really know about its most famous feature, the Great Red Spot? Jupiter, in a way that many don't realize, plays a crucial role in protecting our solar system, acting like a cosmic guardian. It's truly time for us to dive deep into all of its mysteries. This giant world sits just beyond the main asteroid belt, nestled comfortably between the orbits of Mars and Saturn. Its average distance from the Sun is about 778 million kilometers, which is roughly 5.2 astronomical units. From that position, it takes Jupiter approximately 12 Earth years to complete just one trip around the Sun. The planet's axial tilt, that slight lean it has, is quite small, only about 3 degrees. This means that, unlike Earth or Mars, Jupiter doesn't really experience much in the way of seasonal changes. It's quite similar to Saturn in that regard. Its radius, when measured at the equator, is noticeably larger than its radius at the poles, giving it that slightly squashed appearance common to rapidly rotating gas giants. It really is a massive planet, the biggest one in our entire solar system. To give you a sense of its scale, its mass is about 1,000th that of our Sun. Now, that might not sound like a huge number at first glance, but once you consider that the Sun holds onto an incredible 99.86% of all the mass in the solar system, you begin to grasp that Jupiter accounts for almost all of what's left over. Its mass is truly immense, more than 2.5 times the combined mass of all the other planets in our solar system put together. This enormous mass leads to a fascinating celestial dance, a phenomenon involving something called the barycenter. When we typically picture one object orbiting another, we often don't think much about the gravitational pull the smaller object exerts on the larger one. Most of the time, this effect is so tiny, so negligible, that we can pretty much ignore it. Think of the International Space Station circling Earth, or even Mercury making its way around the Sun. But the influence is always there, even if it's minuscule. A barycenter is essentially the center of mass for 2 objects that are orbiting each other. It's the precise point in space around which both objects actually revolve. With Jupiter, given its massive size and its specific distance from the Sun, its effect on our star is far from negligible. As Jupiter swings through its long orbit around the Sun, both Jupiter and the Sun perform a subtle, synchronized dance around this shared center of mass. And here's the truly wild part for the Jupiter-Sun system. This barycenter point is actually above the surface of the Sun. It's located about 1.68 solar radii from the Sun's very center. To help visualize this, imagine holding a long stick with a very heavy object on one end and a lighter object on the other. To keep the stick perfectly balanced, you wouldn't hold it exactly in the middle. Instead, your hand, representing the barycenter, would need to be much closer to the heavier object. Now picture that heavier object as the Sun, the lighter one as Jupiter, and the stick as the invisible force of gravity connecting them. That point where you balance the stick, the barycenter, is precisely where the Sun and Jupiter both orbit around. Even though Jupiter boasts the greatest mass of any planet in our solar system, it's actually not the densest. It simply has the most mass because it's so incredibly large. If Neptune were the same size as Jupiter, for example, then Neptune would actually be the most massive planet. Conversely, if Jupiter were shrunken down to the size of Earth, our home planet would be over 4 times more massive. As it stands, Jupiter's diameter is about 11 times bigger than Earth's, and its total mass is a staggering 318 times greater than Earth's. We all know that mass directly influences gravity, and Jupiter's immense mass means it has a truly powerful gravitational pull, more than twice that of Earth's, at a comparable surface, levels where the atmospheric pressure equals Earth's at sea level. Jupiter's gravity is about 2.528 g. This incredible gravitational strength is so influential that it subtly affects every other planet in the solar system, to varying degrees. It's strong enough to rip apart incoming asteroids and has even managed to capture at least 67 moons. Some scientists even propose that Jupiter's gravity played a role in the ancient past, destroying numerous celestial objects and preventing other planets from fully forming in certain regions. One interesting example of this influence is on the asteroid Vesta. Scientists even speculate that Jupiter's significant gravitational presence throughout the solar system is slowly disturbing Mercury's already elliptical orbit. Over several billion years, this perturbation could potentially cause the tiny planet Mercury to either plummet into the Sun or be completely ejected from our solar system altogether. Right now, however, Jupiter acts more like a hero for the 4 inner planets, including Earth. Without its enormous gravity working as a kind of cosmic vacuum cleaner, it wouldn't be so effective at sweeping up dangerous objects like long-period comets, or at least nudging their paths enough to kick them out of the solar system entirely. Jupiter, as the 5th planet from the Sun, is about 5 times farther away from our star than Earth is. Despite this vast distance, it can appear as the 3rd brightest object in our night sky, outshone only by the Moon and Venus. It can get so bright, in fact, with a maximum visual magnitude of about 2.94, that it can actually cast faint shadows on Earth. Because it's so prominent and easy to spot, Jupiter makes a fantastic target for amateur astronomers. With improvements in consumer telescopes over recent years, it's truly incredible what details people can observe from their own backyards. So, what creates those famous, intricate patterns we see on Jupiter? The cloud layer itself is surprisingly thin, only about 50 kilometers thick, and it contains ammonia ice crystals, much like Saturn's clouds. However, the vibrant coloration comes from chemical compounds that heat up deep within Jupiter's interior and then rise. These compounds are known as chromophores. When they reach the upper cloud layers, they interact with the Sun's ultraviolet light, resulting in those spectacular, multicolored bands we observe. This process is a continuous cycle, and Jupiter's appearance can actually change quite dramatically over time. Even if the specific colors shift, the general latitude of these bands tends to stay consistent enough for scientists to give them specific names and designations, though their width can certainly vary. Where these colorful bands meet, there's a lot of storm activity and turbulence. This chaotic interaction is actually the driving force, the engine, behind Jupiter's most famous and enduring feature, the Great Red Spot. This storm is absolutely enormous, so vast that the entire diameter of Earth could easily fit inside it. It's been observed for as long as we've had telescopes, first documented in the 17th century, leading many to believe it might be a permanent fixture of the planet. Interestingly, however, it has noticeably shrunk in size since those initial observations began. The exact reason for its distinctive reddish color remains a bit of a mystery. The spot's hue can vary significantly, from a deep brick red to almost white at times. The most current theory suggests that chemical compounds are being broken apart by the sun's UV light, a process similar to what happens across the rest of the planet's atmosphere. The storm itself actually sits much higher in the atmosphere than the surrounding clouds, which means it gets more direct interaction with sunlight. This could explain why its color often appears far more intense than anything else around it. But the Great Red Spot isn't Jupiter's only scientifically interesting storm. Another, sometimes called Red Spot Junga, formed when three smaller storms merged into a single, larger one between 1998 and 2000. So far, it has managed to survive unscathed by its much larger neighbor and has become a pretty prominent feature on the planet. It could potentially last for several more centuries if it avoids the same fate as a similar storm that was swallowed by the Great Red Spot. Now, let's consider what we believe Jupiter is made of. Much like Saturn, beneath its thick atmosphere, Jupiter is thought to have layers of gaseous, then liquid, and eventually metallic forms of hydrogen. As you venture deeper into the planet, the pressure becomes incredibly immense. Under such extreme pressure, hydrogen actually behaves like a metal. Below that, scientists theorize there's either an icy or a rocky core. Because we can't replicate the colossal pressures found inside Jupiter here on Earth, we don't truly understand the specific properties these materials exhibit at the very core. Roughly 90% of Jupiter's total mass is thought to be hydrogen, about 10% helium, with tiny, trace amounts of other elements like methane and ammonia. Jupiter spins incredibly quickly, faster than any other planet in our solar system, completing a full rotation in just about 10 hours. But since it's not a solid body, it doesn't rotate at the exact same speed everywhere. A full rotation at the poles takes about 5 minutes longer than a rotation at the equator, a phenomenon called differential rotation. When I was younger, I often wondered why Jupiter wasn't a star. It's so massive, and it's mostly made of hydrogen, which is certainly flammable. Surely, I thought, someone just needed to toss a match in to ignite it. The reality, sadly for my inner child, is that stars don't quite work that way. Plus, there's hardly any oxygen on Jupiter, which is essential for combustion. Stars generate their immense heat through nuclear fusion, a process driven by the extreme pressures found at their cores. The current scientific consensus is that Jupiter would need to be roughly 75 to 85 times more massive than it is right now to have enough gravity and internal pressure to initiate nuclear fusion and become a star. However, it's interesting to note that Jupiter's overall volume isn't too far off from the smallest known red dwarf stars. And yes, you might have noticed in some images that Jupiter actually does have rings. They're nowhere near as grand or visible as Saturn's, but there are 4 distinct planetary rings. The main ring is quite thin but relatively bright, while the others are very wide but exceptionally faint. The main ring is about 6,000 kilometers wide, and one of its only distinctive features is a noticeable notch. These rings are mostly made of dust, unlike Saturn's icy rings, and are thought to originate from impacts on Jupiter's small inner moons, like Metis and Adraste. Something else really important about Jupiter is its remarkably strong magnetosphere. It's about 14 times more powerful than Earth's, largely thanks to the planet's liquid metallic hydrogen core. This makes it the strongest magnetosphere of any planet in our solar system, surpassed only by the Sun's sunspots. There are a couple of really interesting consequences of this. First, magnetospheres act to channel solar wind particles towards the planet's poles, which then produces magnificent auroras, much like Earth's northern and southern lights, but far more powerful. Second, Jupiter's 4 largest moons, often called the Galilean moons, are protected from this solar wind because they orbit within this vast magnetosphere. This means they don't necessarily need their own strong magnetospheres, as Jupiter provides that shielding for them. However, this protection doesn't extend to radiation. Jupiter actually has an incredibly powerful radiation belt surrounding it, a zone so intense that it has severely damaged or crippled every probe that has ventured through it. Io, the closest large moon to Jupiter, passes directly through the heart of this radiation belt, receiving an astonishing 600 rads per day on its surface. To put that into perspective, a human exposed to that much radiation would likely perish within about 4 hours. So, it's certainly not the most welcoming home away from home. Speaking of the Jovian moons, I'll only touch on them briefly here, as they warrant their own deep dive. Jupiter has at least 95 known natural satellites. Many of these, around 51, are smaller than 10 kilometers in diameter. But the largest ones, the Galilean moons, are some of the biggest moons in the entire solar system. These are Io, Europa, Ganymede, and Callisto, and each one is uniquely fascinating. Ganymede, for instance, is actually the largest moon in the solar system, even bigger than the planet Mercury. With that final thought, let's take a moment to consider Jupiter, as seen through infrared light. This view clearly demonstrates the immense size and raw power of this planet. Look closely, and you might spot a small dot at the bottom of the planet. That's actually the impact site of an object from space. If something of that magnitude had hit Earth, it could have potentially spelled the end of our planet, as we know it. We can certainly be grateful that Jupiter is there, not just for its incredible beauty, but because in so many profound ways, it truly is an asset to our solar system. Most of us are familiar with how the planets appear in visible light: Saturn's pale golden hue, Jupiter's striking red bands and colorful clouds, Neptune's deep blue. But planets also emit or reflect light in wavelengths our eyes can't perceive, like infrared and ultraviolet. What we can observe in these other wavelengths is often far more valuable to scientists than just a planet's natural appearance. That's because certain features invisible to our eyes might become very clear in infrared or ultraviolet, and vice versa, if we want to understand what substances are present on a planet. The electromagnetic spectrum offers crucial clues. To begin, let's revisit how Jupiter looks in visible light. The various spacecraft that have journeyed past Jupiter have consistently shown it to be an incredibly beautiful world. In visible light, you can immediately make out much of Jupiter's main cloud deck. These aren't water clouds like those on Earth, but rather clouds made of ammonia ice. If you observe closely, you can start to distinguish the different altitudes of these clouds. The darker, narrower regions are actually shadows cast by the taller, lighter colored clouds. It appears that the higher these clouds are in the atmosphere, the brighter they become, which is evident in the highest altitude, pop-up clouds that often appear snowy white. The exact process behind the distinct colors in Jupiter's atmosphere isn't fully understood yet. However, it's generally thought to be caused by the upward movement of compounds that originate deep within Jupiter. As these compounds rise to the highest parts of Jupiter's atmosphere, they suddenly become exposed to the sun's ultraviolet radiation, which causes them to darken. Eventually, they sink back down into the lower atmospheric layers. But, as we can plainly see, Jupiter's ammonia cloud deck is largely opaque. We can't simply look through it. If visible light were our only tool, the vast majority of Jupiter's interior would remain a complete enigma. Fortunately, we have instruments capable of seeing beyond the limits of our eyes. In specific infrared wavelengths, we can truly see Jupiter in an entirely new light. Perhaps one of the most striking ways to observe Jupiter is by using the 4.68 micron wavelength. This particular view reveals the planet's heat in a very interesting way. In images captured at this wavelength, like those from the Gemini Observatory, it's the lower, altitude reddish bands that appear the brightest. This is because Jupiter actually emits more internal heat than it receives from the Sun. The planet is slowly contracting in size, and this contraction generates heat. This internal heat eventually makes its way out of the planet, passing through the cloud deck. The heat escapes most easily where the cloud deck is thinnest. This explains why features like the Great Red Spot and the white bands, which are bright in visible light, appear dark in these infrared images, as they represent areas of thicker, cooler clouds that block the heat. Fortunately, we're not limited to just a disk view of Jupiter. Thanks to the Juno spacecraft, which is currently orbiting Jupiter, scientists have been able to view Jupiter's poles in infrared. Using this infrared data, they constructed a detailed 3D map of the incredible, swirling vortices found there. Jupiter's North Pole, for example, features 9 seemingly constant vortices, 8 arranged in a square shape, revolving around a larger central one. Again, you'll notice that the lowest, altitude regions are emitting the most heat. Because this specific wavelength primarily reveals heat, the atmospheric haze and shadows don't obstruct the view as much as they would in visible light. This gives us an unprecedented, clear perspective of the 3D structure of these complex vortices. Even in these warmest areas, the temperatures are still quite cold by Earth standards. The yellow sections in these infrared maps are only around 3 degrees Celsius, while the darker, higher altitude regions plunge to 83 degrees Celsius. And because this heat emanates from Jupiter itself, this infrared view is available to Juno regardless of whether it's day or night on that part of the planet. It doesn't rely on sunlight. Storms can even show up in infrared images before they're noticed in visible light. For example, a comparison of images taken by the Hubble Space Telescope revealed near Earth-sized storms located beneath the cloud tops that were significantly warmer than their surroundings. This suggests that Jupiter's internal heat plays a substantial role in generating these atmospheric disturbances. While we're discussing this particular wavelength, let's briefly look at Jupiter's volcanically active moon, Io. Unsurprisingly, Io's night side is brilliantly illuminated by the sheer amount of volcanic activity across its surface. This makes it very easy to identify new volcanoes and keep track of the ones we already know about. Juno has captured several views of Io, each one revealing it to be a hive of activity. A truly hellish yet captivating world. In fact, all of the Galilean moons have been examined in infrared, but using very specific wavelengths that can reveal different aspects. Take, for instance, This infrared view of Europa, captured by the Galileo probe in the 1.5 micron water band. When we observe an object through this particular wavelength, we can pinpoint locations where water is present. The deep blue areas in the image indicate regions of very pure water ice, while other colors suggest a mixture of water ice with other minerals. This technique is called spectroscopy, and it allows scientists to determine the molecular composition of a planet or moon without ever having to land there. It works because when white light reflects off a certain atom or molecule, that molecule will absorb a specific band of light while reflecting the rest. By analyzing the missing light band, we can identify the molecule. So, think of this image less as a traditional photograph and more as a visual representation of data, indicating the presence and distribution of certain molecules, with colors arbitrarily chosen by scientists to represent that information. For example, if we look at this image showing the absorption band for sulfuric acid on Europa, it's the brighter regions this time that highlight where sulfuric acid is most abundant. This concentration of sulfuric acid is found around the cracks on Europa's surface, suggesting it might originate from the subsurface ocean beneath the crust. It's also prominent on the Moon's trailing side, visible in the upper left of the image. It appears that as Europa orbits Jupiter, it is constantly bombarded by sulfur ions. Incredibly, this sulfur likely comes from the volcanic eruptions on Io. If we examine a crater on Callisto, infrared data has been layered onto a visible light image. Here, reds indicate more water ice, while blues show less. This is quite interesting because it's one of the highest resolution infrared images we have of any body around Jupiter, with this specific image covering only about 200 kilometers. It adds a lot of information that wouldn't be apparent from the visible light image alone. Specifically, there's a clear concentration of water ice within the crater itself, but then a distinct ring directly around it where no water is present. Water then reappears in the ray system, extending outwards from the crater. The icier regions likely result from the impactor exposing ice beneath the surface. However, the reason for the water-free ring between the central crater and the ray system's debris is still a bit of a mystery. Perhaps the icy debris from the impact didn't begin to settle on the ground until it reached that particular distance. In any case, this image clearly demonstrates that non-ice materials make up only a thin layer on Callisto's surface. Now, what does Jupiter look like through various infrared bands? This particular image is quite telling. The top left and top right images were captured at 1.621 and 2.73 microns, respectively. In these bands, we can observe the cloud deck in a way that's similar to what we see in visible light. However, the image in the middle is exclusively showing us Jupiter through 2.17 microns, which is the absorption band of hydrogen. As we know, Jupiter is predominantly made of hydrogen, meaning the hydrogen in the atmosphere suddenly becomes opaque and clearly visible at this wavelength. In fact, the only features still visible are the very highest altitude clouds, the ones that poke through most of the hydrogen in the atmosphere. The bottom left image shows the 3.01 micron band, where there's some absorption, but not as much. At this band, it's methane and ammonia that are absorbing the light. The bottom middle image is another heat map, captured at 4.99 microns. Finally, the bottom right image is a false color combination of all 5 of these images. This illustrates what's happening whenever you see a false color image in these kinds of videos. Now you understand what these false color images are trying to reveal. The final interesting view of Jupiter I want to show you is in the ultraviolet spectrum, specifically through absorption spectroscopy. Ultraviolet absorption spectroscopy isn't typically super useful in general planetary astronomy. The only time I can recall it being actively used on Jupiter was to track the impact of Comet Shoemaker, Levy 9, back in 1994. In that event, the comet dust absorbed a lot of the sun's UV light, allowing scientists to easily track winds in the planet's stratosphere by observing how these features evolved. However, molecules that are hot enough will emit light across many different wavelengths. And there's a strong source of light coming from Jupiter in both ultraviolet and infrared its auroras. Jupiter's auroras are incredibly powerful compared to Earth's and are a permanent feature on the planet. The Hubble Space Telescope, which can see in ultraviolet, has been monitoring Jupiter's auroras for years. Though, the very best views have come from Juno in the infrared, simply because Juno's polar orbit takes it directly over the planet's poles, whereas Hubble's viewing angle makes such observations more challenging. These auroras are heavily influenced by Jupiter's magnetic field environment, which funnels streaming particles into its upper atmosphere. They're also impacted by the flux tubes that connect Jupiter with its moons. So, there you have it, a look at Jupiter in a very different way than you might be used to. As you can see, studying absorptions and fluorescence through spectroscopy can help us understand a planet far more deeply than visible light alone can. We can identify molecules and minerals, map a planet's heat distribution, and observe auroras interacting with the planet's magnetosphere. All of these different pieces of information, when put together, help us build a more complete picture of how a planet works and why it behaves the way it does. In July of 1994, scientists around the globe watched in absolute astonishment as Comet Shoemaker, Levy 9, slammed into Jupiter. The force of these impacts was so enormous that it unleashed energy equivalent to 300 million atomic bombs. For 6 days, Jupiter was pummeled by 21 separate impacts from the comet's fragments, which created gigantic plumes of debris that soared an incredible 3,000 kilometers above the cloud tops. This was an impressive feat, considering Jupiter's immense gravity. The impacts also heated Jupiter's atmosphere to temperatures reaching an astounding 30,000 degrees Celsius at the moment of collision. The comet itself was traveling at a blistering speed of 216,000 kilometers per hour, with its largest fragment measuring about 2 kilometers in diameter. These impacts generated huge clouds of debris that remained visible for months and left scars on Jupiter's atmosphere, even more prominent than its great red spot. Collisions of this magnitude aren't entirely unheard of. Our solar system is littered with evidence of massive impacts from comets and asteroids. Scientists believe Earth was struck by a huge asteroid at the end of the Cretaceous period, an event that likely led to the extinction of the non-avian dinosaurs. However, these kinds of events are extremely rare, meaning the chance to actually witness one in action is a once-in-a-lifetime opportunity. So, what did it all look like? And does this incident offer any insight into the probability of a similar event happening here on Earth? In 1993, astronomers Carolyn and Eugene Shoemaker, along with David Levy, were conducting research at California's Palomar Observatory when they made a remarkable discovery: a periodic comet that had been captured by Jupiter's gravitational pull. Periodic comet is one with an orbital period of less than 200 years. This was quite unusual, as most comets in our solar system primarily orbit the Sun. However, given Jupiter's immense mass, being by far the largest of the 8 planets, its ability to capture other objects that approach its orbit isn't surprising. Many of Jupiter's irregular moons are likely captured asteroids and comets that have since lost their volatile surface materials. But this comet had other peculiar characteristics. For one, it was enormous. Scientists estimate that similar impacts from objects this large occur only about once every 6,000 years. The comet was also fragmented, most likely torn apart by Jupiter's tidal forces during a previous close approach. Most striking of all, though, was its highly eccentric orbit. Eccentricity measures how much an orbit deviates from a perfect circle, with 0 being a perfect circle, and 1 being the upper limit, where an elliptical orbit becomes hyperbolic. Shoemaker, Levy 9's orbit, had an eccentricity of over 0.998, meaning it was incredibly eccentric. Almost immediately, astronomers realized there was a possibility the comet would collide with Jupiter. This suspicion quickly turned into certainty once they gathered more precise data. Before long, astronomers knew the impact would happen sometime in July 1994, and soon, the whole world was eagerly anticipating the event. Leading up to the impact, astronomers kept a close eye on the comet's movements, using instruments like the Keck Observatory, Germany's Ara-6 Ray Telescope, and NASA's Hubble Space Telescope, among others. But when the first of the comet's fragments struck on July 16, 1994, it seemed like the worst-case scenario had occurred. It looked as though we would miss the spectacular show. You see, Shoemaker, Levy 9's trajectory meant the impact would happen on the side of Jupiter, facing away from Earth. This meant none of Earth's powerful telescopes were in a position to view the initial collision. For scientists, this would have been a crushing disappointment. But as luck would have it, not all our observational instruments were located on Earth. By sheer chance, NASA's Galileo spacecraft, launched in 1989, was only about a year away from Jupiter at the time of Shoemaker, Levy 9's final approach. It just so happened to be in a perfect spot to record the impact as it unfolded. But Galileo wasn't our only helper from afar. The Ulysses spacecraft, launched in 1990 to monitor the Sun, was also pointed towards Jupiter. Even NASA's Voyager 2, located an astounding 44 astronomical units away, was programmed to monitor radio emissions from the crash site using its ultraviolet spectrometer. Each of these probes temporarily paused its primary mission to collaborate and help us witness this extraordinary event. Shortly after Fragmenta hit Jupiter, Galileo observed a massive fireball erupting, reaching temperatures as high as 24,000 degrees Celsius. Its plume rapidly rose 3,000 kilometers, which would make it roughly the size of Australia from north to south. This was quite surprising, as scientists hadn't expected to see such prominent fireballs in the aftermath of the collision. A few minutes later, vast amounts of ejected debris plummeted back towards Jupiter's surface and burned up again, turning Jupiter's atmosphere into a raging inferno. Before long, Jupiter's rotation brought the impact site into view of Earth, allowing powerful telescopes like Hubble to observe a huge dark spot on Jupiter. As it happens, Jupiter's rotation is remarkably fast, with days lasting only about 10 hours. Contrary to what you might expect, larger planets often have shorter days than smaller ones. The comet's impact generated shock waves that rippled across Jupiter's dense atmosphere at an incredible speed of 450 meters per second. And all of this was just from the very first impact. For 6 days, between July 16th and July 22nd, the comet's numerous fragments relentlessly bombarded Jupiter. The largest impact occurred on July 18th, when fragment G struck. This single impact alone produced a blast 600 times more powerful than the world's entire nuclear arsenal, leaving behind a huge dark spot that was 1 Earth diameter across. However, as spectacular as the initial impacts were, the aftermath of the comet proved just as valuable. By studying the clouds of debris, scientists gained an unprecedented window into Jupiter's atmosphere and its dynamic movements. Additionally, they caught a never-before-seen glimpse of Jupiter's composition beneath its dense cloud tops. Spectroscopic readings were able to identify materials that had been splashed upwards by the comet's impact. They detected diatomic sulfur and carbon disulfide, along with heavier elements like silicon, iron, and magnesium. Interestingly, they also found substantial amounts of water, something they weren't necessarily expecting to see so prominently. In fact, one of NASA's Juno probe's main objectives is to pinpoint where this water is located within Jupiter's atmosphere. However, one of the more unsettling implications of the impact was the stark realization that large celestial bodies could still strike planets. One school of thought had theorized that major comet and asteroid collisions were far more frequent earlier in the solar system's existence. But Shoemaker, Levy 9 made it undeniably clear that very destructive collisions remained a distinct possibility. Was this event a random stroke of luck, a glimpse of an extremely rare occurrence? Or do such impacts happen more frequently than we previously thought? Remember, we've only had the technology to observe this kind of event for about the last 80 years or so. If a comet as large as Shoemaker, Levy 9, were to strike Earth, it would undoubtedly lead to the extinction of most life on our planet. This realization had a dramatic effect on our collective consciousness, as anyone who lived through the 1990s can attest. It also served as a wake-up call for NASA and various defense agencies. Before Shoemaker, Levy 9, the term planetary defense didn't even exist. But in its wake, NASA took on the mission of monitoring near-Earth objects, or NEOs, with the goal of identifying over 90% of asteroids in our celestial neighborhood larger than 1 kilometer in diameter. Having largely achieved this goal, NASA is now well on its way to identifying asteroids greater than 140 meters. But before you start staying up all night worrying, understand that these events are undoubtedly rare, and there's perhaps another silver lining to Shoemaker, Levy 9's impact. You see, Jupiter is a massive planet with an incredibly powerful gravitational influence. And since it's also one of the outer planets, some scientists now believe it might act as a kind of cosmic vacuum cleaner. We know that Jupiter experiences approximately 2,000 to 8,000 times as many cometary impacts as Earth. So, perhaps one of the reasons extinction-level impacts are so uncommon here on Earth is that Jupiter has been a magnet for these kinds of comets and asteroids. This argument has even become a component of the rare Earth hypothesis, which proposes that Earth possesses a unique combination of conditions, without which the evolution of complex life would be impossible. Not everyone agrees with this hypothesis, though, and in any event, we're still a long way from definitively proving it. So, while we might not know the exact likelihood of a massive comet or asteroid hitting Earth, the impact of Shoemaker, Levy 9 with Jupiter certainly advanced our understanding of these dramatic events. Moreover, it was, without question, a spectacular moment that treated observers to one of the most impressive action scenes ever witnessed by human eyes. Maybe one day we'll have the chance to see something even bigger, but hopefully from a safe distance. While there have been other explosive events, such as the 2022 Tonga volcanic eruption, for now, The winner is clear. The biggest explosion ever seen on a planet is still Shoemaker, Levy 9, and by comparison, most other events look like mere drops in the bucket. While the major planets often grab most of the attention in school and from space agencies, there are smaller, less known worlds in our solar system that are just as fascinating. 4 of these are known as the Galilean moons, Jupiter's 4 largest satellites. Considering how close together they orbit, they are truly remarkable because they are so incredibly different from each other. You have a moon that is a volcanic powerhouse, a moon that offers one of the best chances of harboring life out of anywhere else we know, the largest moon in the entire solar system, and an ancient, heavily cratered moon whose surface can be traced back to the very beginning of the solar system. Let's begin with Io, the innermost of these 4 moons. To understand Io's context a little better, it's worth remembering that Jupiter has at least 95 known moons so far. A few of these orbit very close to the planet, within and around its faint ring system. Beyond those are the 4 large moons known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. From innermost to outermost, these moons are Io, Europa, Ganymede, and Callisto. Beyond them are Jupiter's irregular moons, all of which orbit much further out than the Galilean group. Io orbits incredibly close to Jupiter, only about 350,000 kilometers above Jupiter's cloud tops. This means that from Io's surface, Jupiter would appear an astonishing 39 times larger in the sky than our own moon appears from Earth. Io completes an orbit around Jupiter in a mere 42.5 hours, a stark contrast to our moon's roughly monthly orbit. Due to its close proximity, at certain points in its orbit, the tidal bulge on Io is thought to reach up to 100 meters. This effect is similar to the ocean tides we see on Earth, caused by our moon, although on Earth, the effect is far more minimal, with tides usually shifting only about 2 meters from high to low. Io experiences a tidal force that is 300% greater than what our moon exerts on Earth. This is because of its close proximity to the most massive planet in the solar system, Jupiter, and the constant gravitational tugging from the other large moons in the system, which prevent Io's orbit from ever becoming perfectly circular. This means Io isn't going to get any respite from these intense forces anytime soon. A day on Io is the same length as its orbital period, meaning Io is tidally locked to Jupiter. Just as we only ever see one face of our moon from Earth, only one face of Io is ever visible from Jupiter. Io is quite a substantial moon. Although it's the second smallest of the Galilean moons, it's comparable in size to Earth's moon and shares a similar density, meaning its gravity is similar. Interestingly, however, it boasts the highest density of any other moon in the entire solar system, one of its many unique characteristics. Another is that it's primarily composed of silicate rock and iron, much like the terrestrial planets and our moon. This is in contrast to most other large moons in the solar system, which are often made of water ice and silicates. In fact, Io has the least amount of water of any known body in the solar system. Its core is likely made of iron or iron sulfides, surrounded by a silicate, rich mantle and crust. The core is not thought to be convecting, however, as no significant magnetosphere has been detected around the moon itself. The mantle is believed to be liquid near the crust and is at least 50 kilometers thick. This is the region where all the incredible volcanism originates, which brings us to perhaps the most fascinating aspect of Io, the hundreds of enormous volcanoes scattered across its surface. Before the 1970s, we didn't know much about Io at all. although telescopes were starting to pick up faint clues that the moon was devoid of water and that its surface might be composed of sulfur. The first mission to observe Io in any real detail was Pioneer 11, though the image quality was still not great. What it did detect, however, was that Io was made of silicate rock, not water ice, and that it possessed a thin atmosphere. Pioneer 10 was also supposed to capture some close-up shots of Io, but these images were lost due to Jupiter's intense radiation interfering with the onboard command system. The radiation Pioneer 10 encountered was 10,000 times stronger than the maximum radiation levels around Earth. The next missions to Jupiter were the Voyager 1 and 2 spacecraft in 1979. Voyager 1 flew by at a distance of only 20,000 kilometers and was able to capture some truly impressive close-ups of Io's surface. What it revealed was a remarkable landscape, bursting with vibrant colors and a complete absence of impact craters. It discovered mountains taller than Mount Everest, along with volcanic pits hundreds of kilometers wide, and what appeared to be vast lava flows. Most notably, however, it observed plumes erupting from the surface. This provided undeniable proof that Io is volcanically active, and it remains the first and only place beyond Earth where this has been visibly seen, not including cryovolcanoes. Voyager 1 also confirmed that Io's surface is covered in different sulfur frosts. This is what gives Io its many spectacular colors. It found that these sulfur compounds dominate the moon's thin atmosphere. Voyager 2 also observed Io in July 1979, though from a much greater distance of 1 million kilometers. Despite the distance, it still saw 7 of the 9 plumes Voyager 1 had observed in March, indicating that those volcanoes had likely remained active throughout those 4 months. The really interesting images came with the Galileo spacecraft, which arrived at Jupiter in 1995. This spacecraft wasn't specifically designed to extensively study Io, but it did manage to acquire some of the highest resolution images we now have of its surface. Sadly, Galileo never operated at its full potential due to several mechanical malfunctions, meaning we could have had even better images had it been fully operational. What it was able to see, though, were plumes from many volcanoes, as well as confirming that these volcanoes were erupting sulfur and silicate magmas, similar to what we find on Earth, except Io's magma is also rich in magnesium. Io's surface is spectacularly colorful. The yellow plains are primarily composed of sulfur. The white areas are mostly fresh sulfur dioxide frosts. Towards the poles, the sulfur is damaged by radiation, which is why the poles appear redder than the rest of the planet. In other places, the colors of red are deposits left by volcanic plumes that reached hundreds of kilometers above Io. The most obvious of these deposits is from the volcano Pale. Sadly, Pale was inactive when Galileo was in the vicinity, but Voyager 1 was able to capture a massive plume when it flew past. In that image, this plume was an incredible 300 kilometers tall and runs 200 kilometers wide, roughly the size of Alaska. Interestingly, on Earth, the sources of lava flows are typically the depressions you'd usually see at the summit of volcanoes. But these depressions aren't found on high peaks on Io. Instead, you have these vast lava lakes with high walls along their perimeters. Here, for example, is Loki, the largest volcanic depression on Io, measuring 200 kilometers in diameter. These lakes are directly connected to the lava reservoir deep below, but they usually have a thin layer of solidified crust on top. On average, Loki produces about 25% of Io's total heat output. However, sometimes the crust on the lava lake will sink back into the molten material below, causing Loki to suddenly produce 10 times more heat than normal. This phenomenon can be especially seen in Tivashtar, one of Io's other large volcanoes. Normally, this area looks fairly typical, but here, the crust is visibly falling into the lava lake. In this particular image, where there's just white, the radiant energy from the lava curtain was so intense that the camera could only register pure white. In 2007, the New Horizons spacecraft used Jupiter as a gravity assist on its journey to Pluto. It also took the opportunity to test its equipment, focusing its lens on Io during its flyby. What it captured was astonishing. Tivashtar, the volcano I just mentioned, was in full eruption, and its plume could be seen hundreds of kilometers above Io's surface. You can also spot smaller eruptions occurring around the moon. I have to admit, this is one of the most impressive things I've ever seen from space. Even though Io's volcanoes tend to be flat structures, the moon also features some extremely tall mountains, with the highest reaching 18 kilometers. These mountains tend to stand completely by themselves, rather than being part of a ridge or a mountain range. However, many of them are found near lava lakes, indicating the presence of faults in the crust close to these mountains. Another unique aspect of Io is its intricate interaction with Jupiter's magnetic field. Jupiter has an incredibly large and powerful magnetic field, and Io orbits within some of its strongest sections. The unusual thing about this interaction is that when particles from Io's thin atmosphere and its volcanic eruptions are lost to space, these particles don't just disappear. Instead, they form a vast cloud of neutral particles that orbits around Jupiter, known as a neutral cloud. This cloud can stretch far beyond and behind Io's orbit. But that's not all. Surrounding Jupiter is also something called a plasma torus, a donut-shaped region of ionized particles that follows the rotation of Jupiter's magnetic field. This plasma torus rotates much faster than Io's orbit, at about 70 kilometers per second, compared to Io's orbital velocity of 17 kilometers per second. Io orbits directly through the middle of this torus, and the particles from the torus constantly bombard the particles in the neutral cloud, exciting them to higher energy states. These newly ionized particles then feed into the torus, drawn in by the magnetic field lines of the magnetosphere. Particles are lost from the neutral cloud into the plasma torus at an astonishing rate of about 1 ton of matter per second, which significantly increases the size of Jupiter's magnetic field. In fact, if it were visible to our eyes, Jupiter's magnetosphere would appear roughly the same size as the moon in our night sky. Io's interaction with Jupiter doesn't stop there. Jupiter's magnetic field lines, which Io continuously crosses, link Io's atmosphere and neutral cloud to Jupiter's polar upper atmosphere by generating an electric current known as the Io flux tube. A flux tube is basically a concentrated bundle of magnetic field lines. The Sun has these between sunspots, and they're very visible on the Sun due to the charged plasma that flows between them. Io's flux tube creates an aurora trail around Jupiter's poles. This bright point you see here marks where the flux tube from Io strikes Jupiter's upper atmosphere. Auroras are also visible on Io itself, though they're not limited to just the poles. The different colors represent various particles. Being ionized, green indicates sodium, red is oxygen, and blue comes from sulfur. Next up, Europa, one of the most exciting moons in the entire solar system. It's a truly beautiful world, brimming with mysteries. This image is the very first close-up of Europa, captured by the Pioneer probe back in 1973. Since then, we've had the Voyager and Galileo probes explore this moon, and with each visit, Europa has never failed to surprise us. Many of Europa's puzzles are yet to be solved, but we're starting to piece together many fascinating clues. Let's first establish Europa's place within the Jovian system. Europa is the second and smallest of the 4 Galilean moons. Though it's still the 6th biggest moon in the entire solar system, just slightly smaller than Earth's moon. With a diameter of about 3,000 kilometers, it takes Europa roughly 3.5 Earth days to complete one orbit around Jupiter. Interestingly, the first 3 Galilean moons, Io, Europa, and Ganymede, are locked in a 4-2-1 orbital resonance due to their mutual gravitational influence. This orbital resonance, and the constant gravitational tugging from the other moons, prevents Europa's orbit from ever becoming perfectly circular. Because of Europa's slightly elliptical orbit, the strength of the gravitational force exerted on it by Jupiter constantly increases and decreases as it orbits. This creates powerful tides that flex and stretch the moon's surface. These forces are highly significant, as they have a major impact on the moon's appearance and what occurs beneath its surface. Europa's surface is predominantly made of water ice. As you can tell, it looks remarkably distinctive due to its long, continuous fractures and cracks. These features are called lineae, which translates to lines in Latin. These lineae are often only about 1 to 2 kilometers wide, but can extend for thousands of kilometers across the moon's surface. We're not entirely sure how or why these lineae form, but the most likely theory is that as the crust pulls apart from tidal flexing, warmer material from beneath rises to fill the gap, in a manner similar to the mid-ocean ridges we see on Earth. In this image, captured by the Galileo spacecraft, you'll notice some dark brown spots. These are very small, only about 10 kilometers across, and they're known as lenticulae. They are also believed to be formed by the upwelling of hot, less dense material to the surface, either by pushing the existing crust upwards or by breaking through it entirely. Should the underground material have completely broken through, what we then see are these strange, unusual areas called chaos terrains. These are really rough patches, surrounded by a comparatively smooth surface. These chaotic spots are expected to be soft and may contain significant information about what lies beneath Europa's surface, which we'll discuss later. Data from Galileo also suggested that Europa's equator might be covered in icy spikes called penitentes. These vertical blades of ice could be up to 15 meters high and would have formed from direct overhead sunlight striking the equator. Interestingly, penitentes are found on Earth as well, in dry regions at high altitudes, although nowhere near as large as those on Europa. Despite being roughly the same age as the solar system, Europa has very few impact craters. Europa has fewer than 50 major craters, whereas Earth's moon has more than 5,000 craters with a diameter greater than 25 kilometers. This scarcity of craters on Europa indicates that its surface is constantly changing and reforming. Models suggest that Europa's surface is only about 30 to 180 million years old, which is remarkably young in geological terms. Additionally, Europa's icy surface is the smoothest surface of any known solid celestial object in the entire solar system. Its icy crust also boasts an albedo, or light reflectivity, of 0.64, one of the highest among all the moons. Europa's high albedo makes it 5 times brighter than our own moon. The surface of Europa is continuously bombarded by an intense blast of radiation from Jupiter. The radiation level at Europa's surface is equivalent to a dose of about 400 millisieverts per day. Exposure to radiation at that level would be enough to fatally harm a human in a single day. The reddish, brown coloration spread across the moon's cracks and fractures is believed to be due to salt and sulfur compounds mixing with water ice and then being altered by Jupiter's powerful radiation. A recent study from NASA's Jet Propulsion Laboratory even suggests that Europa might glow in the dark. Energetic ions from the radiation penetrate the surface, which would energize the molecules beneath, causing them to release energy as visible light. Unfortunately, we can't observe Europa's dark side from Earth, as we are always positioned between it and the Sun. So we'll have to wait for future missions to Europa before we can confirm this phenomenon. Radiation received from Jupiter also plays a significant role in Europa's atmosphere. Europa possesses a very tenuous atmosphere, composed primarily of oxygen. Unlike on Earth, the oxygen on Europa is formed by radiolysis, which is the process where radiation bombards the water ice surface, splitting the H2O into oxygen and hydrogen. The hydrogen, being very light, completely escapes Europa's gravity, while much of the heavier molecular oxygen remains. The hydrogen and oxygen that do escape Europa's gravity form a dispersed neutral cloud that follows Europa's orbit around Jupiter. In 2012, the Hubble Space Telescope made an exciting discovery: plumes of water vapor erupting from Europa's south pole. This image suggests that these water plumes rise up to 200 kilometers from the Moon's surface. In 2018, astronomers found additional evidence of water plume activity on Europa when they re-examined old Galileo data using a new data analysis technique. A dedicated mission specifically studying these plumes could also help us understand what's inside the Moon without ever having to land on it. This is crucial because what may lie underneath that solid ice surface is perhaps the most fascinating aspect of Europa. There is very likely a global ocean situated between a rocky mantle and the water ice crust. The first hint that this incredible ocean world was hidden beneath Europa's surface came from the Voyager and Galileo probes in 1979 and the late 1990s, respectively. Between these missions, there was a noticeable change in the Moon's magnetic field, which wouldn't be possible unless there was some electrically conductive fluid beneath its surface. Europa's crust also shows signs of a liquid layer beneath it, as it rotates with an angle of 80 degrees, which wouldn't be possible if the crust and rocky mantle were rigidly connected. Instead, it's likely that the icy crust floats on this ocean, and it's believed to complete one full rotation around the Moon once every 12,000 years. The fact that this ocean is not attached to the mantle also helps explain the multitude of lineae on the surface. Tidal flexing should cause lineae to form at specific, predictable points on Europa. Not all over, however, because the position of the crust changes over time, and one spot never stays in the same place for long. More and more lineae are continuously formed. Europa is about 780 million kilometers away from the Sun, which is 5 times farther away than Earth. This means the sunlight reaching Europa is about 25 times fainter. As such, Europa, or any other moon in the Jovian system for that matter, receives very little heat from the Sun. So, unsurprisingly, it's cold enough there that the surface is perpetually frozen. In fact, Europa's surface temperature averages about 160 degrees Celsius at the equator and a frigid 220 degrees Celsius at the poles, keeping Europa's icy crust as hard as granite. However, the powerful tidal stresses exerted on the Moon as it orbits Jupiter generate heat within Europa's core. So, geothermal activity from the core should keep the subsurface ocean in a liquid state. This ocean is believed to be hidden under only 15 to 25 kilometers of solid, frozen crust. The ocean itself is probably about 60 to 150 kilometers deep. Interestingly, Europa is only about 1/4 the diameter of Earth, yet it may contain twice as much water as all of Earth's oceans combined. What's most intriguing about Europa's ocean is that scientists believe it is in direct contact with Europa's silicate rocky mantle. This makes Europa's ocean a potentially suitable environment for life, as we know it to exist. We generally believe that life requires water, minerals, and energy to form. And Europa seems to possess all of these requirements, based on the evidence we've gathered so far. Scientists are extremely confident that this ocean not only exists, but that chemical reactions can take place there, and that there is enough tidal energy heating the core that geothermal activity may exist on this ocean's floor. As we've observed on Earth, entire ecosystems can thrive in such places, far from the sun's light. So, for now, Europa remains one of the most likely places where we might discover life outside of Earth. NASA's Europa Clipper spacecraft is scheduled to launch in 2024 and is expected to reach the Moon by the end of the decade. It's designed to perform more than 40 flybys of Europa. The European Space Agency, ESA, is also working on its own spacecraft, called JICES, Jupiter Icy Moons Explorer, which will explore Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. JUI successfully launched in April 2023 and is also expected to reach the Jovian system by the early 2030s. These probes are specifically designed to examine Europa's water plumes and atmosphere. NASA is also planning a Europa lander mission, but this mission is slated to launch well after the Europa Clipper. These upcoming missions will help us learn more about Europa and, hopefully, confirm the answer to the most tantalizing question of all: does it, or can it, sustain life? At the very least, these missions will provide us with a new perspective on our solar system and help us understand how it functions. So there we have it, almost everything you could want to know about the fascinating world of Europa. Now, let's turn our attention to Ganymede, the third of Jupiter's Galilean moons. This isn't just the largest moon we know of, it's also home to the largest water ocean in the entire solar system. But there's something else that truly sets Ganymede apart from anything else we've encountered before. This Jovian giant contains an intriguing mystery buried deep beneath its surface. As a reminder, Jupiter has at least 95 different moons that we've discovered, and Ganymede is the third of the group known as the Galilean moons. Ganymede is the largest of these 4, boasting an impressive diameter of 268 kilometers. To give you a point of comparison, this is about 0.41 times the size of Earth's diameter, and it's even slightly larger than Mercury, which was previously thought to be the largest moon. Mercury initially appeared bigger because of its thick atmosphere, which stretches hundreds of kilometers into space. But in terms of solid body size, Ganymede takes the lead. Ganymede's volume is even 26% larger than Mercury's, although it doesn't contain as much mass. Ganymede's average density is 1.9 grams per cubic centimeter, compared to Mercury's 5.4. This difference is due to its composition. Like Europa, Ganymede's surface is a thick crust of water ice, extending an impressive 150 kilometers deep. Beneath this icy shell is believed to lie a vast ocean of liquid water. And when I say vast, I truly mean it. While Mercury has very little water and is rich in dense metals, the sheer abundance of water on Ganymede significantly reduces its average density. Ganymede's ocean is so enormous that it contains more water than all the oceans and seas on Earth combined. It's estimated to be an average of 100 kilometers in depth, which is 10 times deeper than the deepest point in Earth's oceans. All this water means that Ganymede is only about 50% rock, with the rest being water and smaller amounts of metals and other ices. This seems quite fitting to me, as the name Ganymede comes from classical mythology, where Zeus Seps, or Jupiter, as the Romans called him, claimed a young boy named Ganymede and took him to be a cup-bearer for the gods. It seems poetic that the moon Ganymede would also carry so much water for Jupiter. Interestingly, Ganymede also possesses a very thin atmosphere that contains oxygen. Now, you might be wondering, with all this water and an oxygen atmosphere, is it possible that life exists on Ganymede? While it's certainly a possibility, there are some features of Ganymede that make this less likely. To begin with, its oxygen atmosphere is incredibly thin. It's estimated to be somewhere between 0.2 to 1.2 micropascals, which is about 100 billion to 500 billion times less than Earth's atmospheric pressure at sea level. That would be impossible to breathe. And while our own planet Earth has certainly shown that ecosystems can flourish in the depths of oceans without sunlight to sustain them, there could be a significant problem preventing this from happening on Ganymede. This is because Ganymede's ocean is so deep that the water at its very bottom would likely be compressed back into a form of ice due to the immense pressure. Life in the deepest parts of Earth's oceans can survive thanks to minerals being ejected from geothermal vents. With such a thick ice layer between Ganymede's core and its ocean, it's unlikely that such venting would occur. Europa, Ganymede's neighboring moon, is generally considered a more promising candidate for life because of this difference. However, if Ganymede's ocean is salty, which there is an increasing amount of evidence for, it could drastically alter the moon's internal makeup. Models suggest that with a salty ocean, there could be multiple layers divided by sheets of ice. If this is the case, the most internal layer could indeed be in contact with the rocky core, potentially increasing the chances of life existing there. But beneath Ganymede's ice and water lies something else truly surprising, something that scientists currently don't have a definitive explanation for. Somehow, Ganymede is producing its own magnetic field. The magnetic field of Ganymede was first detected by scientists in 1996, when the Galileo spacecraft began a series of close flybys of the icy moon. A major indicator of a magnetic field is the presence of auroras, and incredibly, auroras were detected in Ganymede's tenuous atmosphere. Not only that, but as the Hubble Space Telescope studied Ganymede over an extended period, it became clear that these auroras didn't wobble as much as expected, likely a result of something known as magnetic friction. Within a salty water ocean under the surface, a magnetic field is hugely significant, as it's the feature on Earth that shields our planet from harmful solar radiation, enabling all life to flourish. The field around Ganymede doesn't completely protect it from such radiation. Being nestled within Jupiter's incredibly powerful magnetic field and radiation belt means it's still getting bombarded with a lot of radiation. Ganymede's surface still receives about 5 to 8 rem, enough to make a human severely ill or even dead in just 2 months. But it's still better than its closer, orbiting neighbor moons. Scientists are quite unsure why this magnetic field exists at all. Our planet's core is hot and molten, and convection currents within it move electrons, which in turn produces the magnetic field that surrounds us. However, this shouldn't be happening on Ganymede. Ganymede is smaller than Earth, and given its size and composition, scientists believe that its core should have cooled down enough by now to be a solid mass, not liquid. A solid core would prevent the movement of electrons through convection and thus prevent a magnetic field from forming. And none of the other moons of Jupiter have a magnetic field. In fact, Ganymede is the only moon in our entire solar system that has one. So, what exactly is going on? Scientists don't know for sure. But the answer might lie in Ganymede's incredible relationship with its parent planet and neighboring moons, and a process known as tidal heating. Ganymede orbits around Jupiter, roughly once every 7 days in an eccentric orbit. This means that at some points in its orbit, it's closer to Jupiter than at others. When an object comes under a strong gravitational force, it will stretch slightly in the direction of that force as its mass is pulled. However, the further an object gets from the source of gravity, the more it will compress back to its original shape. Since Ganymede has an eccentric orbit around Jupiter, it is constantly coming under more, and then less, gravity, and is therefore continuously stretching and contracting. Have you ever repeatedly pulled and stretched a piece of blue, tack or modeling clay in your hands before pushing it back into a ball shape? If you have, you might have noticed that after a while, it gets surprisingly warm. This is because stretching and deforming material produces friction as the material rubs up against itself. On the scale of moons and planets, this friction generates a significant amount of heat. A tidal force that creates heat through friction is known as tidal heating. On top of that, in a process I find truly fascinating, Ganymede has formed an orbital resonance with 2 of its fellow Galilean moons, Io and Europa, in what is called a Laplace resonance. For each time Ganymede orbits Jupiter, Europa will orbit exactly twice, and Io will orbit exactly 4 times. This mathematically precise configuration hasn't happened by coincidence. It's evidence of the moons, gravities pulling on each other, with the entire system attempting to conserve its resulting momentum. However, it also means that Ganymede is constantly being tugged by its neighbor's gravity, and is under a lot of gravitational stress. So, perhaps this tidal heating is warming up Ganymede enough that its core remains liquid after all, helping it to continue producing its magnetic field. Scientists don't know for sure, but it would perhaps explain why Ganymede's surface is so interesting. You may have noticed that Ganymede's surface is divided into large, dark regions that cover about 1/3 of its surface, and lighter regions that make up the other 2/3. By examining the number of impact craters on these 2 sections, scientists can determine that the dark regions are actually older than the lighter ones, as they contain many more craters. The lighter regions might have fewer craters, but they do feature long ridges and grooves, some up to 700 meters high and thousands of kilometers long. A truly impressive sight. But again, scientists are not entirely sure how these ridges formed. One explanation is that powerful tidal forces stretched out the surface of the moon during an unstable period in Ganymede's ancient history. Perhaps this same tidal force could have also warmed Ganymede's core and preserved its magnetic field. Whatever its cause, Ganymede's magnetosphere has been instrumental in helping scientists understand the moon's composition. By measuring the areas where auroras appeared in Ganymede's atmosphere, scientists were able to confirm the existence of Ganymede's subsurface oceans, all without ever having to physically set foot there. And as for the rest of Ganymede's mysteries, perhaps JUIC, the Jupiter Icy Moons Explorer, will provide us with the answers. The ESA spacecraft launched in April 2023, and although it won't reach orbit around Ganymede for another 10 years after that, Its mission is to investigate the inner workings of a number of Jupiter's moons, including Ganymede. Until then, we may have to let Ganymede's mysteries remain just that, a mystery. Now, let's talk about Callisto. Despite the fact that it's the third largest moon we know of, I think most people would be hard-pressed to recall any facts about it at all. Is it just a boring world? Or do we simply not know much about it? Actually, we know more than you might first assume, and it is far from boring. Let's start with where Callisto fits into the Jovian system. Callisto is the third largest moon in the entire solar system, and it's just slightly smaller than Mercury, measuring 820 kilometers across. However, while its diameter is only 58 kilometers less than Mercury's, it possesses only about 1/3 of the planet's mass, meaning it's significantly less dense, and its gravity is much weaker. Callisto is the second largest of the Galilean moons, and it orbits Jupiter much farther out than the other three, taking about 17 Earth days to complete one orbit, at an average distance of 1.9 million kilometers. Even at this distance, it is still tidally locked with Jupiter, meaning the same side of Callisto always faces its parent planet. However, this greater distance means that it is not locked in an orbital resonance with the other three moons, nor do we believe that it ever was. Callisto has a very tenuous atmosphere, composed primarily of carbon dioxide and possibly oxygen as well, although oxygen hasn't actually been definitively detected yet. We know, however, that this atmosphere is so incredibly thin that the molecules within it rarely collide. Theoretically, this atmosphere should be stripped away by atmospheric loss processes in just about 4 years. Scientists believe that Callisto's crust is continuously replenishing these lost atmospheric particles through the sublimation of carbon dioxide surface ices, evidenced by some interesting surface features. Now, Callisto's surface is one of the most ancient in the entire solar system, with evidence suggesting it's over 4 billion years old. You'll immediately notice the heavily speckled nature of Callisto. Its surface is completely covered with impact craters of various sizes, more so than almost any other object we've observed. In fact, it's close to saturation, meaning any new crater that forms will probably just overlap an existing one at this point, without any significant geological activity. Cratering is perhaps the only process that has dramatically impacted Callisto's appearance over its long lifetime. Why is Callisto's surface so old compared to many other bodies in the solar system? Well, on geologically active planets like Earth, there are numerous processes that can erase almost all evidence of past impacts. Earth has one of the least cratered surfaces in the solar system. Because so much happens on its surface, it has weather, water, plants, volcanism, tectonic plates, and human activity. These forces work together to break apart, wear down, and uplift the ground. Even other Jovian moons, like Europa or Oru, have comparatively fewer craters thanks to the tidal forces, which cause geological activity on their surfaces. This simply doesn't happen with Callisto. Callisto shows no signs of active geological processes, such as volcanism or plate tectonics, and so its surface has remained largely intact after all these billions of years. Limited tidal forces, and thus no geological activity, impact Callisto in another very unique way. There are no mountains of any significant height to speak of on its entire surface. When Callisto initially formed, at the very beginning of the solar system, it was likely an ocean world that has since completely frozen over. And apart from the constant bombardment of meteors, it has stayed exactly the same ever since. So, Let's take a closer look at some of these craters, because some of the biggest ones are truly impressive structures. This is Asgard, the second largest impact crater on Callisto, measuring an astonishing 600 kilometers in diameter. And this is Valhalla, the largest multi-ring impact crater in the entire solar system, with a diameter of 800 kilometers. It's these massive craters that contribute significantly to Callisto's unique appearance, as they contain more rings than craters found anywhere else. With these particularly large craters, the impactor was likely large enough that it may have completely punctured the Moon's thin crust, with the resulting liquid material eventually refreezing over in the lighter patches you see in the middle. Zooming in on these central regions, you'll notice they have a mottled appearance. There seems to be a big difference in contrast between the bright knobs and the darker plains. These regions are significantly less cratered than the rest of Callisto's surface, which would make sense if the plains truly are a refrozen surface, likely making them 2 billion years younger than the surrounding, older terrain. The rings are likely fractures in the crust, a series of concentric failures in the brittle outer shell of the Moon. Interestingly though, within these rings, the bright knobs are still visible. So, what exactly are these knobs? Well, they're believed to be the degraded remains of the millions of crater rims from Callisto's ancient past. We don't know exactly why they have degraded so much over time, but perhaps it's due to repeated micrometeor impacts, or simply that the ice is slowly sublimating over geological timescales. They appear brighter than the lower plains because the rocky debris from the meteors and micrometeors would have gradually fallen down the slopes of the knobs over time, leaving the purer ice exposed at the top. Smaller impact craters on Callisto are also fascinating due to their uniqueness. Most impact craters are shallower on Callisto compared to, for instance, craters on our Moon. Take the Lohi impact structure, for example. It's well over 100 kilometers wide, yet it's only about 600 meters deep. This could be because the impactor was breaking apart before it hit, causing more of a spread out shotgun effect on the surface. Or it could be that the surface has since leveled off due to other, larger nearby impacts that occurred later. This particular crater is believed to be over 1 billion years old, at least, yet you can still clearly see the ejecta that streamed away from the impact. Clear evidence of how unchanging this remarkable Moon is. With some craters, like Har crater, there's even a large dome found in the middle. With typical large impacts on other worlds, you'll often see a few concentric rings and a central peak in the middle. This is very much the case on our Moon. However, Callisto has some remarkable examples of large craters where the exact opposite happens. Look at Tindra here. Instead of a peak, there's actually a pit in the center. Why does Callisto have such unique craters? It could be due to the fact that Callisto's crust is not just brittle, but also relatively thin, with either soft ice or a salty ocean beneath it. Estimates place the crust at about 80 to 150 kilometers thick. The Galileo space probe, which spent several years orbiting Jupiter, dedicated a significant portion of its time to studying the Galilean moons. Galileo discovered that Jupiter's powerful magnetic field could not penetrate completely through Callisto. This implies there is a highly conductive layer under the surface, at least 10 kilometers thick. This couldn't happen in solid ice or silicates unless the ice layer is at least partially molten, or very large temperature gradients can be maintained below the ice to create a conductive effect. Data also suggests that Callisto has a small silicate core at its very center, with a radius of about 600 kilometers. This begs the question, can Callisto be conducive to life, like other icy worlds with water oceans under their surfaces? Well, life as we know it requires liquid water and energy to exist. Callisto might indeed have an ocean of liquid water beneath its surface, but being about 800 million kilometers away from the Sun, it barely receives any heat from our star, and the absence of significant tidal forces doesn't help either, leaving radioactive elements within its core as the only potential source of heat to warm this subsurface ocean, if it truly exists. Unfortunately, even visiting Callisto wouldn't necessarily prove anything immediately. Moons like Europa and Enceladus have visible vents ejecting water directly from their subsurface oceans, meaning we can investigate habitability prospects without ever having to penetrate the oceans themselves. No such vents have been observed on Callisto, so scientists would have to somehow penetrate the thick crust to find out. All these factors combined mean that, unfortunately, scientists currently think that the environmental conditions necessary for life appear to be less favorable on Callisto than on any other icy worlds we're currently studying. Nevertheless, Callisto shouldn't be ignored. If we ever embark on extensive exploration of the outer solar system, Callisto could make a perfect base. You see, orbiting at a distance of 1.9 million kilometers from Jupiter means that Callisto is located beyond Jupiter's main, incredibly intense radiation belt. This makes its environment thousands of times more conducive to human exploration than its inner moons. Callisto also possesses a vast amount of water ice that could be used for propellant production, and, of course, as a staple to sustain human life. Separating the hydrogen from oxygen would also provide oxygen for breathing. Its geological stability would make building structures on the surface relatively worry-free, and the lack of huge mountains or deep trenches means it would be faster, easier, and more efficient to travel across its surface. From Callisto, we could more safely and effectively explore the inner Jovian system from a distance, or use it as a way station for heading further into the outer solar system. Lifting off from Callisto would be ideal thanks to its low gravity, and we could get a gravity assist from a close flyby of Jupiter. It's true that this is a futuristic prospect, but if we ever do become a truly spacefaring species, this is a distinct possibility. While Galileo did an admirable job studying Callisto during its few flybys, there are still many information gaps that need to be filled. With any luck, we'll get that from the European Space Agency's Jupiter Icy Moons Explorers, JUICE, which launched in April 2023 and is expected to reach the Jovian system by 2030. It will explore Jupiter and three of its largest moons, Ganymede, Callisto, and Europa. ESA has planned several close flybys of Callisto during this mission. This mission might provide more insight into questions like, does it truly have a subsurface ocean? And if so, does it or can it sustain life? Beyond that, there are also the questions we haven't even thought to ask yet. Who knows what more we will still discover about this incredible moon? On July 5, 2016, the Juno spacecraft successfully arrived at Jupiter and inserted itself into a polar orbit. This meant Juno has spent years gathering data from around the largest planet in our solar system. So, what has it actually seen? Was it worth all the effort of getting this orbiter to Jupiter in the first place? Well, just take a look at a few of these breathtaking pictures, and then you can decide. Of course, Juno isn't just an expensive camera. It's also been performing several different scientific experiments, and the results have completely changed the way we understand our solar system and Jupiter. So, what exactly has Juno been doing? It's in a highly elliptical and perpendicular orbit, which brings it skimming over the planet at its closest approach, only about 200 kilometers above Jupiter's atmosphere. The furthest point of its orbit takes Juno out over 8.1 million kilometers. Each orbit initially took 53 days to complete, and it was planned to complete 12 orbits by the end of its primary mission in July 2018. At the time this information was first being gathered, Juno had completed its sixth close approach, or Perigove 6, putting it about halfway through its initial mission. Since Juno was in good health, its mission was extended beyond 2018. One of the main reasons Juno approaches so close to the planet is to avoid Jupiter's incredibly powerful radiation belt. There's a relatively narrow gap between where the planet's atmosphere effectively ends and where the intense radiation belt begins, and Juno cleverly exploits this. There was some concern that Juno would still receive a massive dose of radiation from the parts of the radiation belt it does traverse, but the radiation levels were actually 10 times lower than scientists expected in these areas, which was fantastic news for the health of the probe. Do you remember the previous Jupiter probe, Galileo? Galileo faced numerous setbacks due to damage from Jupiter's radiation, as its orbit took it directly through the middle of the radiation belt. So, mission planners for Juno were very keen to avoid a repeat of that as much as possible. Another benefit of Juno's extremely close approach to Jupiter is that we've been able to see Jupiter in truly unprecedented detail. The very first images of Jupiter's poles, in particular, absolutely stunned people. Some even suggested that scientists wouldn't have recognized the planet from these images, as no one expected what they saw. What you're looking at here are numerous cyclones swirling around the South Pole. What's remarkable is how different the planet looks compared to the familiar large bands we're used to seeing on Jupiter. However, the contrast of this image has been significantly enhanced to bring out details the natural eye would perceive something more like this. This particular image is also a mosaic, stitched together from several different images, designed to show daylight across all sides of the pole. The North Pole isn't quite as clear as it was in its winter, meaning some parts of the pole were in constant night. Juno also has the capability to peer deep into Jupiter's atmosphere using a microwave radiometer, an instrument specifically designed for this spacecraft. With it, scientists were able to map the amount of ammonia in the atmosphere. What they didn't expect to see was this distinct band of ammonia around the equator, appearing orange in this image. This pillar of ammonia drops down from the cloud tops over 350 kilometers, which is the limit of what the microwave radiometer can observe. Scientists are very puzzled by this, as they anticipated an even distribution of ammonia throughout the planet, or at least for the gases in the atmosphere to simply mix up or adhere to the familiar band patterns. These results are far from what was predicted, showing just how variable the planet is beneath its uppermost cloud layers. Previously, scientists had theorized that Jupiter possessed a solid core. But using Juno's gravity science instrument, the data suggests something much hazier, or fuzzier, than they would have anticipated. This could imply that the core isn't solid, that it's dissolved, or perhaps that a distinct solid core doesn't exist at all. It may still be some time until we fully understand the truth about this, once all the microwave, radio wave, and magnetic field data have been combined to create a more complete picture. Speaking of the magnetic field, the results from this also came as a surprise to scientists. In some regions, the magnetic field was stronger than they expected, and in others, it was weaker. These patches you see also suggest that the magnetic field is being generated above the planet's core, as it appears quite irregular, perhaps originating within the metallic hydrogen layer. As we know, a strong magnetic field creates auroras, and Juno is equipped with an infrared aurora mapper, giving us views of Jupiter's auroras like we've never seen before. The central band in this animation is the main aurora, and this moving point to the left is caused by Io, the closest of Jupiter's Galileto. Avoid a repeat of that as much as possible. Another benefit of Juno's incredibly close distance to Jupiter at its closest approach is that we've been able to observe Jupiter in unprecedented detail. The very first images of Jupiter's poles, in particular, absolutely stunned scientists and the public. Some even suggested that scientists wouldn't have even recognized the planet from these images, as no one expected what they saw. What you're looking at here are many swirling cyclones around the South Pole. What's truly remarkable is how different the planet looks from the familiar large bands we're used to seeing on Jupiter. However, the contrast of the image has been enhanced to make these details more visible. The natural eye would perceive something closer to this. This image is also a mosaic of several pictures, stitched together to show daytime on all sides of the pole. The North Pole isn't quite as clear in these early images as it was in winter, and some parts of the pole were in constant night. Juno also has the capability to peer deep into Jupiter's atmosphere, using a microwave radiometer, an instrument designed specifically for this spacecraft. With it, scientists were able to map the amount of ammonia in the atmosphere. What they didn't expect to see was this distinct band of ammonia around the equator, appearing orange in this image. This pillar of ammonia descends from the cloud tops for over 350 kilometers, which is the maximum depth the microwave radiometer can penetrate. Scientists are very puzzled by this, as they had anticipated an even distribution of ammonia throughout the planet. They thought the gases in the atmosphere would simply mix uniformly, or at least adhere to the established band patterns on the planet. But these results are far from that expectation, showing how incredibly variable the planet is beneath its top layer of visible clouds. Previously, scientists had predicted that Jupiter possessed a solid core, but using the gravity science instrument, the data suggests a much hazier or fuzzier core than they would have anticipated. This could imply that the core isn't solid, that it's dissolved, or perhaps that it doesn't exist at all. It may be some time yet until we fully grasp the truth about this. Once all the microwave, radio wave, and magnetic field data have been combined to create a more complete picture. Speaking of the magnetic field, the results from this also came as a surprise to scientists. In some regions, the magnetic field was stronger than they expected, and in others, it was weaker. These patches you see also imply that the magnetic field is being generated above the core of the planet, as it's quite irregular, perhaps originating within the liquid metallic hydrogen layer. The magnetic field, as we know, creates auroras, and Juno is equipped with an infrared aurora mapper, giving us views of Jupiter's auroras like we've never seen before. The central band in this animation is the main aurora, and this moving point to the left is caused by Io, the closest of Jupiter's Galilean moons. The tail of the point is the remnant of Io's orbital motion. The whites and greens in this image are from ions striking Jupiter's ionosphere from space, and the reds could potentially be ions originating from the planet itself. If this is the case, it would be a phenomenon never observed before. Most of the data collection takes place only for a few hours per orbit, as Juno rapidly zips past the planet. All the instruments gather as much information as possible during this time, including the camera. This incredible video is a time lapse of Jupiter as Juno approaches the northern hemisphere and then moves away, looking towards the southern hemisphere. This image is a compilation of all the frames used in that video. As Juno approaches the planet, you can clearly see the storms swirling around the North Pole, and gradually the view shifts to the mid-latitudes. Zooming in on some of these shots, we can see the classic swirls and intricate patterns we've come to expect on Jupiter. But if you look really closely, you can also spot these tiny white specks. These specks are actually clouds of water or ammonia ice, as evidenced by the distinct shadows they cast. They are situated higher in the atmosphere than the rest of the cloud layer, and although they appear small, they are actually over 50 kilometers wide. Jupiter is just so incredibly massive that they look tiny from afar. Once you've noticed them, you'll start to see them everywhere. Due to the incredibly freezing temperatures at this altitude where these clouds reside, and because they are made of water ice, it could very well be snowing on Jupiter. Remarkably, we are still learning so much about our giant neighbor. You might have thought that because it's the closest and biggest gas giant, we would have a pretty good understanding of its mechanics. It seems, however, with the arrival of Juno, that we still have a lot to learn, and there are likely questions we haven't even thought to ask yet, let alone answers.